Okay, polynomials. What are they? Well, let's start with monomials. So monomials are just a single term. So something like x to the fifth, maybe 2 times x to the fifth. That's a monomial. Another one would be 3x. Another one would be 5x to the seventh. Let's say minus 5x to the seventh. That's fine. Just by themselves, they are monomials. Now, if you put two of them together, 2x to the fifth plus 3x, that is a binomial. Two terms. Trinomial is three terms. So 2x squared plus 5x minus 7, that's a trinomial. Also happens to be a quadratic. And then there's polynomial, which is any of those, but mostly when you have more than those terms. So 3x cubed minus 7x squared plus 4x minus 1/2. That's a polynomial. All right. Okay. So polynomial is multiple terms of powers of x, I should say, well, powers of x multiplied by a coefficient. So the term 3x cubed, well, maybe just to make it clear, to use the same number, 3x to the fourth this is the coefficient, that's the power, and that is the variable, x, usually, but it can be any letter or symbol you want to have, just not a number. Okay, so the degree of a polynomial is the highest power. So if we had 5x to the seventh plus 3x squared plus 7x, then the degree is 7. All right. Now, as it kind of turns out, we kind of view polynomials, we write them in various ways over time. And so the number of terms can actually kind of vary depending. We've already seen this, say, with quadratics, where you can start with 3 terms, and then when you complete the square, you kind of get 2 terms. If you think of the, like, in the vertex form, the like x minus something, that quantity squared, you can kind of think of that thing inside as one term. You can actually replace the variable with another variable to make it so. So you might argue that it could be trinomial or binomial. So the number of terms we don't worry about too much. What we do worry about is the degree. The degree, that's, that's a defining characteristic of it. Something that's to the square power is different than something to the cube power. We'll go into the importance of that leading power term, but the degree really defines a lot about the power of the polynomial. All right, so what do these things look like? Well, they're going to look like something like this. Okay, that was pretty bad. They're going to look like something like goes up, down, up, down, up, down, up, down. And they can either go from say negative infinity to plus infinity, or from plus infinity to negative infinity, or plus infinity kind of dance down around here and then go back up to plus infinity, or negative infinity dance negative infinity. It can have real roots. It can have no real roots. It can have a number of these maximums and minimums. There's only so many maximums and minimums and roots that polynomials can have. We'll mention that too. But those are some of the defining features. There's also a feature that we generally only talk about in calculus of, if you notice, like here, it's kind of like a upwards polynomial, and over here it's kind of like a downwards parabola. And so somewhere around here is what we call an inflection point. And that's where it changes from being this, collecting water to dumping water. That's so those are kind of the major points of a polynomial. So what is it doing far away from the origin? Is it going towards infinity or negative infinity? It will look like the leading term, the highest degree term, far away from the origin. And then near the origin, it'll have the maximums and minimums and the roots, the zeros of the polynomial. And so we care about that. Later on in life, we care about the inflection points. And then we care about finding, you might want to find the roots, but you can also maybe want to find out like where the polynomial is 5. It's the same process as finding the roots. And those are kinds of questions. Why do polynomials arise? Why do we care about them? Well, that's a somewhat tricky question. Lines and parabolas happen a lot when we're looking at things locally. And then as we kind of pull out from that, polynomials kind of fit better because, for the most part, it's, experience we have we in real life are things with multiple variables. Even thinking of the surface of the Earth, you got things above and below and stuff, and so, it's multidimensional. But if you just kind of think of a road going along and it goes up and down, and so the height of the road could be the value of the polynomial, and where along this road you are, that would be the x. And so that's a way of representing something in the real world. It's got ups and downs, and so polynomial is a reasonable thing to model that with. And then you might want to say, okay, well, if, what can I say about the height, and what's the tallest point, what's the lowest point, when is it at sea level, whatever. So those are the kinds of things, like, we're modeling reality with polynomials. They come about in those fashions. There's also lots of other kinds of functions we'll talk about, and polynomials help with computing those values of those functions. They kind of simulate and represent those functions in ways that we can handle. Polynomials are nice because all it involves is multiplications, either between the coefficient and the x part, or computing the powers. These powers are always positive integers, or negative integers, I suppose. The natural numbers. 0, x to the, I should say this. Oops. X to the 0 is 1. So it's just defined that way. I mean, anything to the 0 power is 1 except for 0 to the 0. We just assume it's going to be 1. It's convenient for notation. Doesn't really mean anything, but just assume. This allows us to talk about, so something like 5x minus 7 is also 5x minus 7, x to the 0, right? And so you can say powers of x for the whole thing. Just a convenient mathematical notation. Anyway, so you have these non-negative powers of x. They're being multiplied together. Then you multiply them by coefficients, and then you add and subtract those terms. And that's it, right? That's the arithmetic. Multiplication, addition, subtraction. And of course, you might have division in there in the sense of something could be a fraction. X could be a fraction. The coefficient could be a fraction. X can be a real number, in fact. In fact, the coefficients can be real numbers. So you still have multiplications of those things. So you have some division in there. But we're not dividing by x yet. That's a whole other thing. Although we will, I should take that back. We will explore dividing polynomials by polynomials. But we'll have a certain different perspective on that for now, and then later on we'll view that as actually new functions. But for now, the functions we're talking about are just polynomials, and when we do the division, it'll be to write it in different forms. So that's big overview. One thing I guess I should, just to make sure we're all on the same page, is let's look at 3x to the 4th minus 7x squared. We'll call that p of x. All right? And what do we want to do with that? Well, we may want to graph it, compute things with it. So this is what the graph looks like. This is symmetrical around the y-axis, so you can flip it because we just have even powers. So we've got kind of the min here. Then we have a maximum here, and we have a minimum here. So this is a 4th degree polynomial. It's got 3 extreme points, the local max, local min, but notice, okay, so here these local mins are actually the lowest point of the function. It never goes below those points. But this local max, it it is not the maximum. There is no maximum of this function. It goes on forever into the plus infinity. We also have 1, 2, 3 zeros, but this is actually kind of a double zero. So there's actually kind of like, in our minds, we're going to say it's 4 zeros. All right. And then if you want to compute some stuff, so yeah, 0, 0, right? That was plug in 1, we get -4, 2, we get 20, 2.56, that, right? Just computes it all out for us. So let's just see how, well, just get a new page. So p of x equals 3x to the 4th minus 7x squared. All right, so if we wanted to compute, say, p of 2, it's fine, equals 3, 2 to the 4th minus 7, 2 squared. Well, I guess that should be consistent where I put the power. Okay, so this means you take 3 and 2 to the 4th. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's 3 times 16 minus 7 times 2 squared, which is 4. And so this is 48 minus 28, which is equal to 20. P of minus 2 would be 3 minus 2 to the 4th minus 7 minus 2 squared equals the same thing. Why? Because the even powers negate the negative. So minus 2 times minus 2 is plus 4. Things like that. So it's important to understand how to plug in an x value and get out a value. That ideally should be number 1 on the list of things to understand. The other thing we can do with this thing is we can factor it. So this is x squared, 3x squared minus 7. What did I do? I saw that there was an x squared in both terms, and I factored it out. Now, it's a little hard to see the factoring versus checking that it worked. And so how do we check that it works? Well, we multiply it out. X squared, 3x squared minus 7. Oops. Sorry, just 2 terms. X squared times 3x squared is 3x to the 4th. X squared times minus 7 is minus 7x squared. And so that's equal to 3x to the 4th minus 7x squared. Check. Right? So we're looking for things to pull out that we can multiply this stuff together. And furthermore, when you can factor it into something a little bit simpler, we have x squared times 3x squared minus 7, right? So x equals 0. Oh, sorry, equals 0. 0 squared is 0. 0 times whatever 3x squared minus 7 is, that'll be minus 7, but 0 times that is 0, so that's a 0, as we saw in the graph. And this has 2 solutions, so this is 3x squared equals 7, or x equals plus or minus the square root of 7/3. Right? This is just solving a quadratic, which we know how to do. in general, it's not that easy to solve higher degree polynomials, but sometimes it is. And of course, if you're doing K-12 kind of polynomial stuff, they'll probably give you stuff that, factors like this. It's not generally a useful technique in the real world, but it's okay. It's important to actually understand what to do with a factored form. Less important how to get it, because you're unlikely to get it. But if you have it, what can you do with it? How do you assemble a polynomial from the factors? That is useful. All right. Now let's say that, let's do another polynomial. Let's say q of x equals 3x cubed minus 7x squared. Wow, I'm really in a rut here. 5x cubed plus 2x squared minus x plus 2. So that's another polynomial. And, I don't expect anything nice to come out of this. I just wrote it down. Let me just show you GeoGebra's version of what one could do with this. So we can write 5x squared, cubed. And notice as you type it out in GeoGebra, it starts to graph it. I find it kind of annoying, but I'm sure there are people who enjoy that. And then there we go. So that's our parabola. Notice that there's nothing symmetrical about anything. GeoGebra helpfully allows you to take these extremums. So there's the max and the min, local max and local min. Notice there's no global max or min, right? So this function goes on to off to minus infinity and then up to plus infinity. If I were to graph 5x to the cubed, and then I zoom out, right? And wonder if I can, yeah. So I zoom out, and they actually look pretty similar, right? I mean, they'll always be shifted from one another, but that kind of the relative shift, decreases. So when you try to look at it on a big scale, and they do look different, but then as we zoom in, notice our scale here has been kind of wonky. So let's go back to the standard view, and then you can see these differences here. All right. Now our original polynomial here, I only had one root. Okay, so I had a nice root. So this tells me that there's actually a factor here. It goes x plus 1. And then what is this rest of the stuff? Well, I'm going to know that this is 5x squared, and this is going to be 2, because when you multiply these things out, the highest degree term corresponds, and then the no degree term, the 0 degree, goes with that one. And so it's just kind of this middle term that's kind of missing. And so in this particular instance, I could just try to do my little box trick and see what happens. So 5x squared and 2, so I can fill in these things. I've got 5x cubed plus 5x squared, And down here we've got 2x and we've got 2. And now what do we need to do? So 2x adds within the x term, so we want, I'll just write it in red for what we want. We want when it adds, when the 2x adds to whatever's in this box, we want it to end up with minus x, right? So when we add along this diagonal, we get minus x. And to get from 2x to minus x, we need to add in minus 3x. And then the 5x squared here, so that's, we want the 2x squared. So when we add this, this is supposed to be 2x squared. So we need a minus 3x squared. And so that sounds like we need this to be minus 3x. All right, so that's, once I found out that there was a root, I wasn't really going to try this out because I just figured there wasn't, because I just wrote some stuff down. But there was a nice thing. So that's minus 3x. I've deduced it from this thing. You can verify multiplying with the box that it all comes out. But in any event, that's how we do that. And now you've got this polynomial. I mean, it's quadratic. So now there's this quadratic. And that's where the other roots are. And then we can use our techniques with the quadratics on this. But we could also just go over to get a sense of this is 5x squared minus 3x plus 2, like so. And you can see that there's no roots with that. And if you should be reflect about well, anyway, you could find the complex roots from that. There's no real roots from that quadratic, but there are complex roots. Quadratic formula would work. You can reflect the quadratic around its that horizontal line of symmetry and then draw the circle and get it that way. Whatever. I don't really have a need to do that, so I'm just not going to do that. But you can do that. Anyway, so there's 3 roots here, and it's a degree 3 polynomial. But some of those roots were complex, right? So it doesn't necessarily mean you have 3 real roots. You could have 2. You could have complex ones. Complex roots always come in pairs. So the cube is, it has to have a real root for that reason. Also, if you think about it, it's going to change for very large x. We'll talk about this a bit more too. It's negative, large and negative at one point, and then it's large and positive at another point, and it's got to kind of cross that axis somewhere to get from negative to positive, or negative or positive to negative, depending. In any event, so these are the kinds of thoughts that we'll explore with polynomials. This was just kind of an overview and a taste. We'll try to do some specific problems and so forth as we go along. But essentially, these are the kinds of things, graphing, factoring, plugging in values, solving for values. These are the questions, thinking about very large x. And then eventually we're going to start talking about how to rewrite the polynomial in different viewpoints. That's fun too. So that's polynomials. A lot of this is not necessary for, like immediate right now life. Instead, it's setting the groundwork for working with other stuff. There's a lot of interesting functions that come about in life, and polynomials allow us to work with those functions, even though they're not polynomials. So we kind of represent stuff with polynomials, whether they are not polynomials, but they may be things we care about are well represented by polynomials. Polynomials are very flexible and can fit anything that's kind of nice and smooth, which for the most part reality gives us nice and smooth stuff. We don't have too many things, or at least gives us pieces that are nice and smooth. Anyway, that was kind of a rambling overview of polynomials, and now we'll start digging down into them in more depth.